Welcome back, folks. This is Mr. Johnson with you once again. This is the second of two lectures on Le Chatelier's principle, the first being about the general concept of that principle and how that principle applies to concentration changes. This will be a continuation of that conversation where we will look at the effect that changing volume/pressure has on equilibria, and as well the effect that changing temperature has on equilibria. We are on page 120 of our physical textbook, 128 of our ebook. Looking at section 2.3 here, how equilibria respond to volume and temperature changes. I'd like you to try this warm-up on your own to begin with. And pause the video, come on back and see how your answers compare to mine. Again, try this warm-up here at the top of this page to start you off. All right, scientific meaning of pressure, or the formula/definition for pressure, is a force exerted over an area. For us in here, pressure applies primarily to gases. It's the force that the collective gas molecules exert over the area, the container in which they exist. Gas pressure, of course, is due to how many gas molecules there are. The more molecules there are hitting the walls of a container at any given time, the greater the force. As well, the faster they're moving, the greater the temperature, the greater the kinetic energy, the greater the force they exert over that given area. To increase gas pressure, I wasn't quite sure what to put here, but I said compress the gas into less space or force the gas into less space. And typically that'll be to decrease the volume of the container. We increase gas pressure as a result. What is temperature a measure of? It's the average kinetic energy of the molecules, remember? And kinetic energy is 1/2 times mass times velocity squared, which is why two gases that are at the same temperature, which would therefore have the same kinetic energy, won't be moving with the same velocity, because more massive gases would have a lesser velocity with the same kinetic energy as lesser massive gases. And then finally, an increase in temperature increases the rate of reaction because the molecules collide more frequently. They're going to hit the walls of the container more often, and because they're moving faster, they'll collide with more force. And before we get deeper into that section, I wanted to jump back to 2.2 and to the definition of Le Chatelier's principle to remind you what again it says, which is that an equilibrium system subjected to a stress, remember a stress is anything that can be done to a system that affects the forward and reverse rates differently. So subjected to a stress will shift to partially alleviate the stress and restore equilibrium. We know already, for example, that an equilibrium system, if a reactant is added, something on the left-hand side, the system will respond to remove some of that additional reactant by shifting to the right, by converting some reactant into product. Meanwhile, if a reactant was removed from an equilibrium system, the system would shift to regenerate some of that removed reactant, and it would shift left to do so, converting some product into reactant. We're now going to look at how that comes into play with volume, pressure, and temperature changes. We're going back to 2.3 now. All right, so we're back on 120 of the textbook, 128 of the ebook, looking at this section titled How Equilibria Respond to Volume Changes. Think of volume changes as the same as pressure changes, because if we increase the volume of a system, the pressure will drop. That applies to both gases and solutions. If you increase the volume that gases are in, the pressure that gases exert on the wall will drop. If you increase the volume that solutes are in, if you increase the volume of the solvent, the volume of the solution, there's a lower concentration of solute than in that solution, and there's also what is considered to be lower osmotic pressure. So increasing the volume of a system, if it has dissolved ions in it or gases, decreases the pressure, whereas decreasing the volume of a system increases pressure. All right, if we read this statement here in bright, beautiful pink, it says, equilibria respond to volume changes by shifting to relieve some of the added pressure or to replace some of the lost pressure. So if a stressor is done to a system where the pressure drops, the system will respond in such a way to increase the pressure, to restore some of that lost pressure, and vice versa. Let's see how that comes into play here in a sample problem. All right, we're looking at sample problem 231 on the following page, 121 of our physical textbook, 129 of our ebook. It says the system described by the equation below is compressed. The volume has been decreased, it's been compressed. Therefore, the pressure will be greater. In what direction will the system shift to restore equilibrium? And when equilibrium is restored, how will the number of each type of molecule and the concentration compare to those before the system was compressed? One thing to notice is that there's 2 moles of gas molecules on the left side, the reactant side, and 1 mole of gas molecules on the right side. We are supposed to know that if this system were to shift to the right for some reason, then there'd be a conversion of 2 moles of gas molecules to 1 mole of gas molecules. There'd be fewer gas molecules if this system were to shift to the right, and that would decrease the pressure. Again, this system shifting to the right would decrease the pressure. On the other hand, if it were to shift to the left for some reason, 1 mole of gas molecules would be converted into 2 moles, and 2 moles exerts greater pressure than 1 mole. It doesn't matter what the types of gases are, their masses, pressure is directly related to moles. All right, so let's apply Le Chatelier's principle to this question. The system is compressed. The volume has been dropped. There's a greater pressure now in this system as it's been compressed. The system will shift in such a way to alleviate that stress, to decrease the pressure a bit. By compressing it, the pressure has increased. The system responds to alleviate that and to decrease the pressure. Well, that is caused by shifting to the right. Converting 2 moles of gas molecules to 1 mole of gas molecules would decrease the pressure, would alleviate that stress. And if we see here under the solution, it says the system must shift to the right to reduce the pressure. Next question, how will the number of molecules change after the system has reached equilibrium? Well, if it's shifting to the right, there will be fewer reactant molecules, there will be fewer PCl3 and Cl2 molecules, and there will be more PCl5 molecules. Fewer reactant molecules, more product molecules. Meanwhile, the system was compressed, the volume decreased. So that increases the pressure and concentration of everything in the system to begin with. By decreasing the volume, the concentration of the reactant and product gas molecules will increase. Meanwhile, the system then shifts to the right to decrease the concentration of reactant molecules, but it will still be greater than it was to begin with. Because remember, when systems shift, they do so to alleviate some of the stress, but not all of it. So there will still be a higher concentration of reactant molecules because it's been compressed and it's only shifted partially to the right. And then certainly there'll be a higher concentration of the product molecules than there was before the system had been stressed. So I've just scrolled up and I'm looking at this section here in green, which illustrates a really important point to us. If we look at this equilibrium system, we see that while there are 2 different types of reactant molecules and only 1 type of product molecule, there are the same number of moles of molecules on both sides. There's an H2 and an F2, 2 moles on the left and 2 HFs on the right. There are an equal number of moles of gas molecules on both sides. So if this system were to shift left or right for some reason, that wouldn't change the number of gas molecules in the system, and it wouldn't change the pressure. Meaning, if this system is stressed by increasing or decreasing the volume, it will not respond, because shifting left or right will not change the pressure. Again, when there's the same number of gas molecules on both sides, there will not be a response to pressure/volume changes. All right, I'm going to walk you through another sample problem, but this one involves dissolved ions instead of gases. Remember, for dissolved ions, you can think of as increasing the volume, meaning adding more solvent, making the total volume of the solution greater, the same as increasing the volume of a system with gases. If you increase the volume of the solution that has dissolved ions in it, you're decreasing the pressure or decreasing the total concentration of all those ions. All right, let's read this problem. System below is diluted. Water is added to it. All the ions will be at a lower concentration. In what direction will the system shift to restore equilibrium? And when it's restored, how will the number of each type of particle and the concentration compare to before? So similar type of question, but now we're dealing with dissolved ions, and the volume is becoming greater by being diluted. We want to notice something similar with this system as we did before. There are 2 dissolved ions on the reactant side, but only 1 dissolved ion on the product side. If this system were to shift to the left for some reason, that would increase the concentration of dissolved ions. That would raise the pressure, something called osmotic pressure, which you don't need to worry about in here. If the system were to shift to the right for some reason, converting 2 ions, dissolved ions, to 1, that would drop the concentration of ions and drop the pressure. So we want to think about that as we contemplate the answer to this question. Something else, this system will only respond to pressure/volume changes if there's a different number of ions on each side, which there are. There's 2 on the left, 1 on the right, so it will respond to this stressor. All right, so we know already the system has been diluted. That means the system will respond in such a way to increase the concentration of ions / increase the pressure. That's going to be achieved by shifting to the left. By converting 1 dissolved ion into 2, there'll be a greater concentration and a greater pressure. to alleviate that stress. And that's what we see here. It's going to shift left. Meanwhile, product are being converted to reactant. So there'll be fewer product ions, fewer HNO2 ions dissolved, and more H plus ions and NO2 ions dissolved. Decrease in HNO2, number of particles, increase in H plus and NO2 ions. Similar to last time, because the entire system is being diluted, the concentration of all of the ions will be lesser once equilibrium is reached than they were beforehand. The HNO2 ions will be the lowest because it's shifting to the left, but again, all of the ions will be at a lesser concentration once equilibrium is reached. All right, I've scrolled down. I'm on practice problems 2, 3, 1 on this same page, and I encourage you to answer practice problems 1 and 2 on your own. Write your answers down in your book. Pause the video, come on back when you're done, and compare your answers to mine. All right, if this first system is compressed, that means it's going to increase the pressure. The system will respond in such a way to decrease the pressure to move to whichever side has fewer moles of gas. That's the left side, so it will shift left. Meanwhile, if it shifts left, there will be more NOCl molecules, reactant molecules, than there were at equilibrium, and fewer NO and Cl2 molecules at equilibrium. But because it's being compressed, even though the system shifts left, all of the reactant and product particles will be at higher concentration, so higher concentration of everything. Number 2 is diluted. That's decreasing the osmotic pressure, decreasing the concentration. This system will shift in such a way to increase the concentration, increase the pressure, and that's going to be to the side with more dissolved ions. That's going to be to the right. System will shift right. Meanwhile, that will decrease the Ag(S2O3) sub 2, 3 minus ions, and increase the silver and S2O3, 2 minus ions. Because it's being diluted, all of the particles, all the reactant and product ions will be at lower concentration at equilibrium than they were before. So the next question to consider is why. Why do these stressors, in this case pressure or volume changes, cause equilibrium systems to shift the way that we have been able to predict that they do? I want to remind you that a stressor is something that can be changed about an equilibrium system that affects forward and reverse rates differently. So I always want to think about that. Is it the forward rate that's increasing more than the reverse rate? Is it the reverse rate that's maybe decreasing more than the forward rate? And then how does that cause that shift to occur? Up here in orange it says, and the phrasing of this is a little awkward at first, the direction, forward or reverse, that has the greater sum of gaseous or aqueous reactant coefficients is the more sensitive of the two directions to volume changes. And that doesn't tend to make sense until we look at an example. By more sensitive, we mean that a volume change will decrease or increase the rate that direction more than of the opposite direction. So we're going to go to a sample problem to see how that plays out. So we're going to come back to the first practice problem we just did to explain why it shifts left. We know it shifts left. Why? Well, looking at this system, we know that there are more gas particles on the right than the left. Whichever side has more particles is more sensitive to rate changes. Set that aside for a moment. All right. If we know this system is compressed, the particles, reactant and product particles, will be at a higher concentration than they were before. And if they're at a higher concentration, the rates of the forward and reverse reactions will increase. If you decrease the volume of a gas system, increase the concentration, reactant and product particles are colliding more frequently, forward and reverse rates both increase. But it's the product side that has more gas particles on it. Therefore, the reverse rate will increase more than the forward rate. And when the reverse rate increases more than the forward rate, the system shifts left. Again, this system shifts left because there's more gas particles on the product side than the reactant side. Therefore, the reverse rate will increase more than the forward rate. Once again, that's why the system shifts left. Although you tend not to have to explain this next thing, one could wonder, well, why is that? Why would the reverse rate increase more than the forward rate? I've said it's because there's more gas particles, but what's the link there? So let's explore that for just a moment. And that once again comes down to rate laws. If we write the rate law for the forward reaction, R sub F, it's equal to a constant, which we can work as a constant, times the concentration of NOCl squared. Well, if the volume is halved, let's say, or the volume is decreased, because this system was put under greater pressure, the concentration would double. And if the concentration doubles, because this is second order, the rate would quadruple. 2 squared is 4. So the forward rate would quadruple in this hypothetical case. Meanwhile, the reverse rate law is rate law constant times NO squared times Cl. And if this same system were to have the volume halved and the concentration of all these particles were to double, well, double squared is 4x times the doubling of chlorine. 4 times 2 is 8. The rate would go up eightfold. So this is mathematical proof via what we know about rate laws, that if this system has its volume decreased, it's compressed, the reverse rate will increase more than the forward rate because there's more gas particles on the product side than the reactant side. All right, we flipped the page. We're on sample problem 232A here, describing the shift mechanism for a decrease in volume. Looks like we've got 3 moles of gas particles on the reactant side, 2 on the right, so this would respond to a volume/pressure change. Then it says to explain in terms of forward and reverse rates how the equilibrium system would respond to a decrease in volume. Remember, if the volume is decreasing, the pressure is increasing. The system will respond in such a way to alleviate some of that increased pressure, to drop the pressure, to go to whichever side has fewer moles of gas. So it will shift right. Once we've predicted that we'll shift right, we just then have to explain which rate is going up by more. We know that if the volume is decreasing and the pressure is increasing, the forward and reverse rates both increase. It's the forward rate that increases more than the reverse rate, causing the shift to the right because there's more gas molecules on the reactant side than the product side. In summary, compressing the system increases the forward rate more than the reverse rate. That results in a net forward reaction known as a right shift. Down here, we've got this reaction rate diagram that we're comfortable with. At equilibrium, initially at equilibrium, the forward and reverse rates are equal. Once the stressor is added, the forward rate increases more than the reverse rate. They're both greater, but the right-hand arrow is significantly longer than the left-hand arrow. And then over time, those arrows find each other, the forward and reverse rates equal each other, and the system is once again at equilibrium. Realize, though, that both the forward and reverse rates after equilibrium is reestablished will be greater than they were before, because this is in a more compressed system, but they're equal to each other. If we drop down to this sample problem, this is a shift for volume change, but it can be thought of similarly with dissolved ions. How will the forward and reverse rates affect the equilibrium system when it's diluted? Well, if it's diluted, that means that we're adding more solvent and that the system will respond in such a way to increase the concentration of ions. It'll do so by shifting to the left, where there's more ions dissolved. Reactant particles, there's more of on the left. Well, if we dilute a system, decrease the concentration, that always decreases the forward and reverse rates, but it will decrease the forward rate more than the reverse rate because there's more particles on the reactant side, therefore causing this left shift. Again, diluting the system decreases the forward rate more than reverse rate, resulting in a reverse reaction known as a left shift, depicted once again beautifully by this reaction rate diagram down below. I flipped the page, looking at practice problems 232 here in pinky purple. Please try practice problems 1 and 2, write your answers down in your book, pause the video, come on back when you're done and see how your solutions compare to mine.
And I just watched what I'd filmed and realized that I was getting successively smaller in each of the clips. There's a little teeny tiny version of me in the last clip. Anyways, here I am, back maybe, full of life. Not sure how big I am, but I'm feeling small anyways. All right, so in question 1, I said that because the volume is decreasing, that's going to result in an increased pressure. The system will respond in such a way to drop the pressure. So that's going to be a left shift. The reason is that the 2 rates will go up when we increase the pressure, but because the product side has more moles, the reverse rate will be greater than the forward rate. So reverse rate will increase more than forward rate, so there'll be a left shift. In question 2, if there's dilution with ions, that's a decrease in either the pressure or the concentration. So we look for the side that has more moles, that's the product side. Both rates will drop when there's a decrease in pressure or concentration, but the reverse rate will decrease more than the forward rate because there's more moles on the product side, and that's going to cause a left shift if the reverse rate decreases less than the forward rate. Okay, so we're down now to our last stressor, and we're going to look at how it is that temperature changes affect equilibria. We've looked already at how volume/pressure changes cause equilibria shifts, how adding or removing reactants or products cause equilibria shifts. Last one is temperature. All right, so in green here, it says equilibria respond to changing temperatures by shifting to remove some of the added kinetic energy or to replace some of the removed kinetic energy, as we would expect Le Chatelier's principle would say. So if we look at the sample problem here, we see an equilibrium system where the delta H is indicated. In order to determine how a system will shift in response to a temperature change, we need to know if that system is exo or endothermic. Because this delta H is positive, we know it's endothermic. You can think of the word heat being a reactant, because if it's endothermic heat, thermal energy, kinetic energy is going into the system. So to make this a little bit simpler, it's sometimes nice to write or picture the word heat as a reactant, which it would be in an endothermic reaction, or as a product, which it would be in an exothermic reaction. All right, so it says here the system is heated, the temperature is going up. In which direction will the system shift? And when equilibrium is restored, how will the concentration of each of the species compare to what they were originally? All right, so if this system is heated, we know that the system will shift in such a way to remove some of the additional heat. Well, if heat can be thought of as a reactant, which it can in an endothermic reaction, then if this system were to shift to the right, it would consume some of that heat, some of that reactant. And in fact, that's what happens. The system will shift to the right to consume or to get rid of some of the additional kinetic energy that was added. Meanwhile, if this system is shifting to the right, we would expect to see the two reactant concentrations drop, N2 and O2, and the product concentration increase. I've flipped my page, looking at sample problem 233b here. We've got an equilibrium system between nitrogen gas, oxygen gas, and nitrogen monoxide gas. Meanwhile, the delta H is positive, which means it's endothermic, and our book has suggested that we do the same thing I just mentioned, which is think of or picture the heat in an endothermic reaction as a reactant. In this case, the value, 181 kilojoules, is written as a reactant. It says the system is cooled, so the temperature is dropped. In what direction will the system shift? And when equilibrium is restored, what will the concentrations of each of the species be compared to before? So if this is endothermic and the energy or the heat can be thought of as a reactant, if it's cooled, the system will respond to regenerate some of that removed heat. That will be achieved by shifting left to regenerate some of the heat that is thought of as a reactant here. So the system will shift left, and in so doing, the concentration of the product, NO gas, will decrease, and the two reactant concentrations would increase. I've scrolled down. I'm on the same page looking at practice problems 233 here. I recommend that you do both of these on your own in your book. Pause the video and come on back when you've answered these to see how your answers compare to mine. So in this first reaction, the delta H is negative, telling us that it is exothermic. So I either picture or write the word heat as a product. This is an exothermic reaction. Meanwhile, if the system is heated, we know it will shift in such a way to remove some of the additional heat. That would be achieved by shifting left, because that would get rid of some product / the heat that can be thought of as a product. So it'll shift left. Meanwhile, the reactant concentrations, brackets, concentrations will increase. That's the upward pointing arrow. And the product concentrations will decrease. In the second question, it's also exothermic because the enthalpy value is written within the reaction as a product. And if it's cooled, the system will shift in such a way to regenerate some of the removed heat. That's going to be a right shift to get more energy out of it, as energy is a product. So there's a right shift. The reactant concentrations will decrease, and the product concentrations will, that arrow should be upward pointing. The product concentrations will increase. All right, we're getting close to the end here. The last thing we're going to talk about is why. Why is it that the temperature changes we saw in the prior problems caused the shifts that we were able to predict? What is that shift mechanism? Our book leaves a little bit to be desired in its explanation. So I'm going to take you to a few PowerPoint slides that I made that are going to explain to you why it is that those shifts occur due to the temperature changes we saw.
And what's great about the explanation is it relies on things we already know from kinetics that we just need to sort of put together. So we're looking here at a diagram of an exothermic reaction, and we would know it's exothermic because the delta H is negative. The products have less potential energy than the reactants. And as we hopefully already know, the forward reaction activation energy for an exothermic reaction is always less than the activation energy for the reverse reaction, depicted via these two red arrows here.
If it were an endothermic reaction, though, we're looking at the diagram here to the right, where the products have more potential energy than the reactants, the reverse would be true. The forward reaction's activation energy is always greater than the reverse reaction's activation energy in an endothermic reaction. And that's shown here in a Maxwell-Boltzmann curve. This is again for an endothermic reaction where the forward reaction would have a greater activation energy than the reverse reaction. The forward activation energy line is written to the right of the reverse, indicating or depicting that it's greater. Something else ideally we know, and that's going to help explain again the mechanism for these shifts, is that at higher temperatures, the shape of the Maxwell-Boltzmann curve changes. At T2, which is greater than T1, the curve widens, the peak drops, and we see this change again in the shapes of these curves. If we draw this activation energy line, it's somewhat arbitrary at this point, we should know that at a greater temperature, there is a greater percentage of molecules underneath this curve. There is a higher percentage of molecules to the right of the activation energy line, and therefore a greater percentage of molecules that if they were to collide, and with the right orientation, would collide with enough kinetic energy to overcome activation energy. At the lower temperature, however, the area under the green curve, there is a lower percentage of molecules that would collide with sufficient kinetic energy to overcome activation energy. So that's something that we know already, and that will aid us in our explanation. All right, so I'm going to try to take you through an example here. This Maxwell-Boltzmann curve at two different temperatures is meant to represent a reverse reaction for an exothermic reaction. Remember, an exothermic's reverse reaction has a greater activation energy than the forward reaction. So this vertical line, the activation energy, represents the activation energy for a reverse reaction that has a higher activation energy than the forward reaction. Like we talked about already, at a higher temperature, there's a greater percentage of molecules beneath the curve to the right of the activation energy line. I've estimated that under the red curve to the right of the activation energy line represents about 20% of the molecules. So 20% of the molecules at a higher temperature would have enough kinetic energy with successful collisions to overcome activation energy. Meanwhile, I've estimated the area under the green curve to be at about 10%. Based on those estimations, that suggests that at this higher temperature, with 20% of collisions being successful versus 10%, that would result in a twofold increase in the rate. Under this set of arbitrary conditions, raising the temperature would increase the reverse rate twofold due to the percentage of molecules under the curves that increases by a twofold increase. Meanwhile, I've added another line to this Maxwell-Boltzmann curve that's in blue. It's right there. That is to the left of the red line, meaning it represents an activation energy that is lesser than the one that was already drawn in red. This blue line represents the activation energy for the forward reaction of an exothermic reaction, which we already know to be lesser than the activation energy for the reverse reaction. So again, blue line represents the forward reaction's activation energy in an exothermic reaction, which again is lesser than the reverse activation energy. Off to the right here is all the information you've seen already about the percentage of molecules under the curve for the reverse reaction. But if we do this for the percentage of molecules under the curve to the right of the forward activation energy line, we get some different percentages. I've estimated the area under the red curve to the right of the blue forward activation energy line is approximately 30%, and the area under the green curve to the right of the blue forward activation energy line is roughly 20%. So in that case, as the temperature goes up, that represents a 1.5-fold increase in successful collisions, right? 30 over 20 being 1.5, or a 1.5-fold increase in the forward rate. What we're seeing now via these Maxwell-Boltzmann curves is evidence that for an exothermic reaction, when the temperature is increased, there's a greater increase in the reverse rate than the forward rate, and that will always be the case. So that's our shift mechanism. When the temperature of an exothermic reaction is raised, we know it shifts to the left to get rid of some of the additional heat that was added. The reason is that both the forward and reverse rates will increase, but the reverse rate increases more than the forward rate due to the math you see here. But all you need to say is that when the temperature of an exothermic reaction increases, the reverse rate increases more than the forward rate, causing the shift left. Again, the evidence being these numbers. So the general rule about the shift mechanism for temperature changes is that the reaction, either forward or reverse, with the greater activation energy is more sensitive to temperature changes. If a reaction is exothermic, the forward activation energy is lesser than the reverse. Meanwhile, if a reaction is endothermic, the forward activation energy is greater than the reverse. If we raise the temperature of a system, both forward and reverse rates will increase. But whichever reaction has the higher activation energy increases more. Meanwhile, if we drop the temperature of a system, both the forward and reverse rates will decrease, and whichever reaction, forward or reverse, has the greater activation energy will decrease more. So with this slide depicting an exothermic reaction, as we know, the activation energy of forward reaction is lesser than activation energy of reverse. If we were to raise the temperature, both the forward and reverse rates would go up, but the reverse rate would go up more than the forward rate because the activation energy is greater. And that's what it says here. Meanwhile, if we were to lower the temperature of this system, both the forward and reverse rates would go down, but the reverse rate would go down more than the forward rate because the activation energy is greater, causing the right shift that we know to be true. Same explanation for endothermic. I just wanted you to see a model of it. In an endothermic reaction, the forward activation energy is greater than the reverse. So if the temperature increases, both the forward and reverse rates increase, but the forward rate increases more than the reverse because the activation is energy, causing the right shift we know to be the case. Meanwhile, if the temperature is dropped, both the forward and reverse rates decrease, but the forward rate decreases more than the reverse rate because, again, it has a higher activation energy, causing the left shift we know to happen. So now I'm going to solve a couple problems with you, give you a couple of practice problems, and then we'll wrap this video up. All right. Asks us here on this sample problem, page 136 of our ebook, 128 of our textbook, to explain in terms of forward and reverse rates how the system would respond. It's not just asking us to state the shifts, but to explain why we see that shift. Well, delta H is positive, so we know this is an endothermic reaction. We could picture the word heat on the left-hand side. We should know that an endothermic reaction has a greater activation energy for the forward reaction than the reverse. If this system is heated, we know that to get rid of some of that additional heat, it's going to shift right. Heat can be thought of as a reactant. And the reason why is that both the forward and reverse rates will increase when a system is heated, but the forward rate will increase more than the reverse rate because, again, the forward reaction has a greater activation energy, causing that right shift. And that's what we see in our explanation here. Diagram is depicting that. At equilibrium, the forward and reverse rates are equal. Once the stressor is added, the temperature is increased. The forward rate increases more than the reverse. Both those arrows are longer, but the forward arrow is much longer than the reverse arrow. And at some point, they find each other and equilibrium is reestablished. As we scroll down, we've got another equilibrium system that is cooled. Meanwhile, it is endothermic, so we could picture the word heat as a reactant. If it's cooled, we should know that both of the forward and reverse rates will decrease. But because this is endothermic, the forward rate will decrease more than the reverse rate, causing that left shift. So cooling the system decreases the forward rate more than the reverse rate, causing a shift to the left, depicted once again by this beautiful reaction rate diagram. All right, almost home. Last little bit here. Practice problems 2, 3, 4 on the following page. Try 1 and 2, please, on your own. Write your answers down in your book. Come on back when you're done and see how you did. All right, the first one, it's an exothermic reaction. Heat could be pictured as a product. If it's heated, we know that both forward and reverse rates will increase, but whichever reaction has the greater activation energy increases more. In an exothermic reaction, we know the reverse rate has a greater activation energy, so the reverse rate will increase more than the forward rate. There'll be a left shift. In this second problem, it's endothermic. We've got the enthalpy value written as a reactant. If it's cooled, we should know that both the forward and reverse rates will decrease. But in an endothermic reaction, the forward activation energy is greater than reverse, so the forward rate will decrease more than the reverse rate, causing the left shift we expect from cooling an endothermic reaction. That is it, folks. Thanks for hanging in there. I appreciate all the hard work you're doing. I believe it's worth it. Give yourself a hug and love the people around you. Take care.